Okay, so now we're going to spend a little bit of time thinking about encodings. So we're going to assign an encoding. That's a piece of fancy jargon here in engineering. And what we're going to do is we're going to come up with a representation. In this case, in our case, a binary representation of possible messages to all the different sort of messages I need to send. So in the case of a coin flip, conceptually, I want to send either heads or tails. An encoding would say 0 I'll use for tails and 1 for heads, and so forth and so on. And sometimes there's very obvious encodings. In other cases, the encodings are much less obvious. It depends on all the engineering goals. And here, if we look down at the bottom, you can see that depending on what our goals are, we may come up with different encodings. Okay, so if we want something that's very simple, we want to come up with an encoding that means that our machinery for transmitting and receiving the encoding actually involves as few components as possible. That may be a measure of, help us influence what we choose as an encoding. We may want to have the encoding be very efficient. We may want to come as close to the entropy bounds as we can. If we're paying for bandwidth from the rings of Saturn to send pictures back from Cassini all the way back to Goldstone to receive those beautiful close-up pictures of the rings, well, we have to use we have a fairly modest power budget. We have to be very careful about how much power we spend. We don't want to send one more bit over half of the solar system than we have to. So now we're interested in being very efficient in our encoding. We may hope that things are very reliable. It would actually be nice to get a picture back from Saturn that wasn't mostly just noise because of all the corruption that happened all the way across the solar system as the message made its way to us. We hope might be secure. Okay, so those are all different sort of alternatives you have to think about when picking an encoding. Mostly for our purposes, we're going to be very interested in coming up with sort of concentrating on the efficiency and the reliability, and we're going to talk about those in turn now for the last 20 minutes here of the lecture. 15 minutes. Okay, now in terms of something that's really simple, fixed length encodings are often the best answer. And in fact, they're sort of the only, in a sense, sensible answer when everything is equally probable. So for instance, if I want to code decimal digits, from 0 up through 9, and I'm going to sort of encode each digit separately, and I'm thinking of building a machine that can manipulate numbers of arbitrary size and so forth and so on. Or maybe back in the old days I was implementing COBOL, which really had the notion of specifying numerical precision in terms of decimal digits. I'm going to come up with, I have 10 possible choices. I'm going to have to use some number of bits. Shannon tells me I have to use at least 3.22 bits, 3.322 bits. If I used only 3 bits, I wouldn't be able to encode all the digits unambiguously. So I'll just choose 4 bits. And that's slightly inefficient, but has the advantages that each digit is now represented separately, so I can ask about the 17th digit of a number without having to sort of understand digits 1 through 60. So fixed length encodings often have this access of allowing easy random access. I can get to the umpteenth part of the message without having to somehow decode the earlier parts of the message, because each part of the message is taking a certain constant size, and I just have to skip over them to the right place, and then I can read what I want to read. How about representing characters? Most of us spend a lot of our day with some sort of character-based representation of information. A very common way of representing information, at least for the last umpteen decades until from the 50s through the early 2000s, was to use ASCII. It's a little 7-bit code representing the sort of the printable characters that you might find, for instance, on a typewriter. Okay. More recently, we've gone to Unicode, which is like a 16-bit representation. Why did we go to Unicode? Why did, now all the programming languages are saying, well, we have 2 types of strings. We have old strings, and we now have Unicode strings, which have these bigger characters in them, the 16-bit characters. Why did we go to Unicode? Yes, sir. We need to be able to represent more than what Americans see when they look at a typewriter. We want to see what the Russians see when they look at a typewriter. Or, well, I won't say the Chinese, because their typewriter would be rather large. But everybody has this notion of what a glyph looks like. That's a representation of the way we represent information sort of graphically on a page or on a screen. And what we're trying to do is come up with a way of encoding which glyph we want to show you or to print out. And basically the world changed. We ended up with a lot more glyphs we want to show you these days. So that's sort of where Unicode came from. So, 7 bits, 16 bits, so forth and so on. Numbers. Of course, we're going to get to numbers. Computers are all about numbers. Number crunching. That's what computers do. So this is something you all learned in 2nd grade, right? We're just going to use a binary representation for a number, which is exactly, the base 2 representation. So, in your modern math class, the math teacher was very pleased to, instead of just teaching you about old-fashioned decimal numbers, you learned about numbers base 8 and numbers base 4 and numbers base 2. So each one of our digits in our representation is either a 0 or 1. And we can write out, and you can see here, in this case, this is the representation of the natural number 2000 as a 12-bit binary number. To see the various combinations here. And you know how to turn bits into their corresponding actual numerical value. You multiply each digit, in this case 0 or 1, times the weight of the column that exists in. And each of the columns are various powers of the base that you're using. And you can come back now with the actual integer that's being represented. So binary representation of the integer 2000, or the natural number 2000. Now, we're going to deal with binary strings a lot in this course. It's handy to writing out very long strings of zeros and ones is hard to read. There's 2 other sort of summary representations. There are also binary representations. They just use either octal digits or hexadecimal digits to represent the same underlying binary pattern. Okay, so in the case of octal, I'm taking groups of 3 binary bits at a time and encoding them using one of the 8 octal digits. We happen to borrow the decimal digits 0 through 7. And the way you can tell a number is an octal, in most programming languages, it starts with a leading 0. That's your key that it's an octal. We can also do the same for hexadecimal. In this case, we start with a number with 0x to remind us that the number is in hex. In hex, we're encoding 4 bits at a time, and we use the hexadecimal digits, which are the 0 through 9 and A through F. Okay. Now, everybody looks at this slide and say, why is Homer a fan of octal? Okay, now the answer is staring you in the face. Okay. Okay. So look carefully at Homer and figure out why Homer was a fan of octal. Okay, so